All right. Good morning, everybody. This is the April. Wow, we're in April. April 6th, CAPN office hours. We have a pretty short agenda, but FaZe, I'll hand it over to you to demo the multi-cluster scheduler that you've been working on. I think I need to make you a host. Give me 1 second.
Yeah, before that, how about just go through the status? I mean, we still, do we have any update? I think.
I'm still working on the why am I blanking on names right now? The nested control plane controller. So the types got merged. Chow, who's not on the call, I basically just put a note into Slack. I'm inclined to merge the API server PR that he has open. I don't know if anybody else wants to give that a quick look before I give it an looks good to me, because it'll just merge once we do that. So if you've already,
so you haven't shipped it, right?
Yeah, it looks good to me. I just don't want to. I don't want to comment that yet in case anybody else has feedback before we go through.
And I will take a look after meeting. If I think it's okay, I'm going to merge it.
Perfect.
Okay. So now next thing is nested
controller manager.
Mm-hmm. Chow is online, so maybe Chow can give a quick update on that. Is that ready or still need some time?
Yeah, I'm still waiting for the nested API server controller to be merged. So after that one is merged, I will rebase and submit the PR for the nested controller manager. It's quite similar to nested API server. So I think it should be ready in 1 or 2 days. Nice. It can be ready in this week. So yeah, if everything is okay, we can merge these 3 nested components all to the master. Yeah. Mm-hmm.
Nice. And I'll probably have the NCP controller tomorrow. By end of day tomorrow, at least a pull request up there, so we can take a look at that, so we can start to converge everything together.
Okay. Right. Yeah, sounds good. Mm-hmm.
Cool.
Then okay, if there are no more agents, I can do a kind of brief description about the multi-cluster thing.
Yep. Let me make you host real quick. Sorry, give me 1 second. All right, you're good to go.
So yeah, let me see. I'm kind of. What should I do? Should I click share screen? Yeah. Okay.
Yeah.
Let me see. Let me try to share this one. What did you guys see?
We can see terminal.
Terminal. Okay. Can you see this one, or can you see this one? Okay.
We can see one that has your root to context in there.
No, can you see the Chrome web?
No, just
one terminal.
Yep.
Only terminal. Okay, so I think I'd better start with some high-level description first.
Yeah, that'd be great.
Sharing screen, and this one. How about now?
Chrome is showing, and you've got the CAPN office hours doc.
Okay.
Perfect.
Yeah, let me actually just come with this figure. Can you guys see this? Okay.
Yep.
Yeah. So some background for the people who may not very closely know what I'm trying to do. The problem was that we have incoming requests. People ask for saying if this system, the VC architecture, can be extended to support multiple superclusters, because our previous design is kind of n mapped to 1. Kind of n means number of the tenants, so it's n mapped to 1 model. The syncer was designed to have a MC controller to sync all the multiple tenant controllers requests into 1 superclusters. So there are quite some use cases for this in terms of supporting multiple superclusters. One is, for example, for the edge computing, they have multiple clusters spread across different geographic regions. So there are some technical issues or whatever management issues. They don't want to combine with a huge generic, just one giant clusters. They're spread multiple small clusters. So do we have a way to utilize the resource of that many clusters? That's always a good question. Another thing is we cannot. So in a cloud company, probably we can somehow assume our supercluster has autoscaler enabled or that capability. But for other companies like on-prem data centers or other use cases other than the cloud vendor, you probably cannot make assumption that the supercluster can be autoscaled. Then in that problem, in that case, you always has a problem such that because we don't expose the detailed supercluster details to the tenant, so tenants always assume they have an infinite capacity, but in fact that's not the case. So how can we scale the supercluster is also another question. So another way of scaling is just give another supercluster. So that is another way of scale the Intel capacity from a capacity perspective. So due to these a few reasons, I'm thinking of, so in the past a few months, I'm trying to see if we can extend the model to support multiple superclusters. The idea is there are a few problems, right? The first problem is how can we change the sinker, somehow support kind of M to N mapping. It's kind of M is number of tenants, N is number of superclusters. So because you need to have a way to do the synchronization between these kind of a multiple entities. I have think of through the possible changes on the sinker. In the end, we have two ways. One way is is kind of we let the sinker to be a kind of two-way MC controller. So one MC controller for tenant, another MC controller for super. That's doable, kind of doable. Another way is kind of like the way that I did in the figure. So we kind of horizontal scale the number of sinkers. So we still use one sinker to take off one superclusters, but there is a one-to-one mapping between sinker and supercluster. So I tend to go this route due to a few reasons. First is so architecture-wise, this is simpler, and the changes to sinker to support to make Intel thing work is minimum. The second reason is that from performance perspective, this has least performance impact. Otherwise, if one sinker is connecting multiple supercluster, you always have contention. You will have another level of contention on the supercluster accesses because you have a centralized hub at the sinker. I don't want to bring too much performance concern on this design. So instead, I tend to go with the multiple sinker approach. Like each one supercluster has one sinker. So another problem is if you look at this way, so you always have a problem in the sense. In the past, it is very clear. If you have a tenant part, it's clear which supercluster it has to. You only have one supercluster, so there's no doubt that there's no scheduling decision here. But now you have a scheduling decision in the sense that you have multiple supercluster. You need to basically decide which supercluster the part should go. This is a kind of, I would say, in all the multi-cluster design, this problem is always kind of ignored or overlooked for whatever reason. Probably one is this is a hard problem. Second is, but without this capability, so every existing multi-tenancy, multi-cluster workload management, the users has to somehow understand the usage of the supercluster or the multiple kind of clusters. So decide, for example, for workload, they need to decide how many replica to supercluster 1, how many replica to supercluster 2. This is the way that KubeFed does. But I want to do this in a kind of more transparent way, in the sense that I want to abstract the entire superclusters, multiple superclusters as one. So from the user perspective, they shouldn't be worried or care about how to distribute the paths, instances across the superclusters, which I think is a kind of manual tedious work, making a lot of automation framework broken. So in a sense, I want to do more intelligent in the sense that if there is a tenant part, we need to the system need to automatically decide which superclass it goes. So for this goal, I want to pretty much we need to introduce another level of scheduling in our framework. That's basically you need to have one scheduler decide which supercluster a tenant part should go, and another level scheduler is in the supercluster itself. So it decides which node the part should go. So this is pretty much the high level from the part scheduling perspective. This is the way that I think it goes, and that this is the model I'm trying to achieve. Another reason I want to, if you look at the figure, I call it a namespace scheduler, which is not a part scheduler. So the reason of doing that is I'm thinking of another route in the sense that if people really want to use the system, again, you still need to, some users still need to tell us the quota, the resource, how many resources they probably need in the first place. Again, because we hide all the supercluster details. Without doing that, it is possible that one user, because this is a shared multi-tenant platform, it's possible that one user, without this quota to enforce kind of capacity planning, it is possible that the user just keeps spawning the job and use up entire supercluster resources, where others just cannot use it. So from the capacity, you still need to have a level of capacity planning. But it's only a capacity planning. There is no scheduling decision. It's just a capacity planning. I think this capacity, this kind of capacity planning is still needed. I'm kind of leverage the existing quota system, and because the quota system is has a tight relationship with the namespace, so I call this kind of namespace scheduler. But in reality, what it does is trying to schedule quota within that namespace across multiple superclusters. This is what the namespace scheduler does. So overall, as this figure shows, essentially people, the general workflow is something like this. So tenant create, so we have a per supercluster syncer, and this syncer can synchronize the tenant object to the corresponding supercluster. And the tenant object need to have label or whatever, tell the owner so which supercluster this object should go, right? And this labeling work is done by the scheduler. And so once the people create a quota within a tenant namespace, the namespace scheduler trying to break this quota into small slices and spread the quota and do the scheduling based on the available capacity of the supercluster. Showing these figures, in this figure just show example. If you look at the red placement, the placement is the scheduling decision, done by the namespace scheduler saying that, okay, this namespace has a quota CPU X, memory Y, and the scheduler tell you this namespace should be placed in cluster 1 and cluster 2. So once we have this label, attached to this namespace, the following things we do is the syncer notice that, oh, this namespace can be placed in C2 and C1. The C1 syncer will create a namespace in cluster 1, and the cluster 2 syncer will create the same namespace in the supercluster 2. So this is the first step. Every time you create a quota and the scheduler tell you the placement cluster the namespace should go, the corresponding syncer will create the namespace in the corresponding superclusters. This is the first step. Then next step, when the part is actually created in the namespace, the namespace scheduler also need to decide which supercluster should go. But now it doesn't need to go through all the superclusters, because the namespace scheduler tell you this namespace, the resource can only go cluster 1 and cluster 2. Now the namespace scheduler only need to decide, okay, within the C1 and C2, which cluster the part should go. This is another steps for the part scheduling. But think about it this way. So because in general, the placement cluster number should be small, and the overhead of doing this step should be small, because even you have, for example, you have thousands of superclusters, but for your namespace, probably only placing a few, very few superclusters that can accommodate all the quota requests. Then this level scheduling just from the 3 clusters, pick one which can satisfy the parts request, and that's it. Then once the part have a annotation say which cluster, supercluster should go, then the syncer will copy that and will sync that part to the corresponding supercluster. And this is kind of in general workflow. Do you guys have questions up here?
All makes sense so far.
Okay, cool. Then I'm going to switch to my console. Let's see. Stop showing. Can you guys see it?
Yep. As long as it's just one terminal.
Yeah, one terminal, yes. Okay.
Yep.
So, all right, so this is the one, the current Kubi config connect to the meta clusters. So basically meta clusters has everything about the VCCR and the cluster CR. So if you guys, I haven't mentioned, but I'm still using VCCR to model the virtual clusters. I'm using the CAPI cluster CR to monitor the to represent our super clusters. I think if you, so yeah, forget about this tenant. So this is probably the wrong one. So if you look at the I think I have one here. Yeah, this is a secret in the super admin. Super admin is the namespace. I'm trying to model the super clusters. So this is the cluster CR. I have two super clusters with different names. That's probably okay. And if you, I have one tenant. So this is the model that this is the model that I show in the figure in the demo. This is the meta clusters. I generated a super cluster using Minikube. So if you look at this is the, so this is the Kubi config to get these two super clusters in the to see the namespace. So I'm going to clear everything. So make sure then I can go from the start. Let's see. I have a this is the way that I can access this is a tenant master. So I have one namespace called default, and I'm using default namespace to do the experiment. If you look at everything, I have now I'm going to go through something like how to clear everything. If you can get deployed, I think I have a deployment here. Yeah, it has 4 ports. Let me try to delete everything. Okay. One quota. Try to delete this quota. Yeah, here I want, as I can see in the VC Manager, I have, besides the VM agent, VC Manager, I have a scheduler running and 2 syncers, 1 syncers per superclusters. Show something, the typical way that I see this one. Oh, too many logs. Let me try to make these things a little bit simpler. Yeah, not too many logs. Try to query. Yeah, give a few time for the scheduler to restart. I want to start with the scheduler. Yeah. So in the scheduler, every minute I'm going to dump Intel on the scheduler cache. This is the description about the cache. The cache have 3 components like clusters and namespace and the paths. So in this case, this is empty one because I just deleted that quota. So there's no namespace being scheduled because the quota is gone. The path is empty, there's no pod is running. So in these dump sets, you only show the 2 root clusters, the status of these 2 root clusters. Some important things like you have how many are allocated, what are allocated items, what is the capacity. So this is from the tenant perspective, basically. From tenant perspective, there is no pod is allocated. The entire capacity has not been used. The rest of things is pretty simple, and this pods tell you what are the pods in these clusters. This provision is the capacity that allocated but reported from the supercluster. So which means you have a schedule. So every time you schedule something, the scheduler cache will update the allocate. And if the schedule decision has been reached to the supercluster by the syncer, the superclusters then then the cluster, the scheduler will update the provision one, saying that okay, this allocation is actually a provisioned to this. There are a bunch of allocations are actually provisioned in the root cluster already. I can explain this a little bit later, but I think this is not affects the overall functionality. This is only I make this design to avoid what case that for the failure recovery, because we will have a case that the supercluster, the tenant cluster is kind of offline for some reason, but the pod is still running in the superclusters. So if when we recreate the Intel the scheduler cache, if we don't get information from the supercluster what are actually running, then our cache will be wrong because we have this capacity, but we are not accounting for the actual usage. The scheduling will be wrong. So that's the reason I introduced this provision and the provision items. Yeah, that's pretty much it is. We have 2 superclusters here, and they are completely empty. Now, if you look at the key is here, we play with the namespace and the quota as a user interface. If you look at this default namespace, then we have an annotation. So this annotation indicates, so for every namespace, if we don't specify, we will use a default slice, but I would recommend people to introduce a slice. The slice indicating the smaller is the scheduler entity for the scheduler. The reason why I introduce slice is I want to avoid kind of fragmentation, in the sense that if people specify a quota with big value, then then if we cannot break down this quota into small pieces, it is highly possible in the supercluster you will introduce the fragmentation. The idea is based on the quota slice and the total quota you are specify. I'm going to calculate how many slices you have. Then the scheduler just trying to schedule this slice across the clusters. So basically, you can think about the analogically is like a memory page. So you have a big memory, but in the end, the operating system, the body system just control the distribution in the sense that if you want your namespace to be scattered to as many superclusters as possible, you probably will make a smaller slice. Then you have a chance to spread more slices to more clusters. Where if you want the namespace to be concentrated to a smaller number of clusters, probably you can make the slice number a little bit bigger. So there are kind of always, this is kind of classical trade-off between the page size, allocation, and fragmentation. So I give you this, so I introduce slides to make this flexibility in our scheduling. Otherwise, it is kind of very strict in the sense that you have to place a big chunk, which is the quota. Sometimes it is hard to find a placement, hard to find the slots to fit this quota, and sometimes it will introduce fragmentation. So this is one key concept that I call it slice. So now next, if you look at the quota, this is the quota I'm going to specify. The quota saying, I'm just using this quota saying that you have a two CPU 200 and the memory 200. If you look at my slice is 100, pretty much if you do this, you are going to place two slices. So what I do is I'm going to okay, now if you look at the namespace again, so you will see this one. So this one is the scheduling results. The scheduler put this scheduling results saying that, okay, you have two, now you have two slices. And I tell you the placements is these two slices go to the root cluster 1. Because root cluster apparently has enough capacity to just hold 200 mini core. It's just mini, I think it's mini core, yeah, and 200 megabyte. Let me see. If you now look at the dump again, you will see now the dump show that I have one namespace being scheduled. This namespace has a quota of 200, but slice has a 200 quota and 100 slice. The scheduling result is put this to root cluster 1 with 2 slices. And if you look at the root cluster 1, you will find that, okay, now it has this many allocated, and the allocated items, what are the items? The items of granularity is a slice. And is actually provisioned in the sense that if you look at the root cluster 1, you will see that this default namespace is synced to the root cluster 1. So which means the actual allocation are provisioned. So because this provision item indicate that in the supercluster, this namespace is actually synchronized to the supercluster root cluster 0001. Okay, now My current design is you can change the quota. So, and we will do the rescheduling. So this is a kind of something slightly different with part scheduling is like, the immutable results. Once part scheduler node, you cannot change it anyway. But I think in this model, you have to provide this functionality. People should be able to change the quota if they want. So in current design, I allow people to change the quota. For example, if I do this, if I change the quota from the 200 to 400, see that now I have 4 slices, and our scheduler, we are going to change the scheduling results because you have 4 slices. I'm going to spread these 4 slices to 2 superclusters. One supercluster has 3 and another supercluster has 1. Once you do this, if you look at the supercluster 2, you should see that supercluster 2 also synchronize this, have created a namespace, the synchronous namespace. And if you look at the logs, I hope it will wait. Sometimes it print every minute. Okay. Now you can see that the supercluster Y actually has three allocated items. Each item, the unit is the slice. So because they have 3 slices, and the root cluster, root 2 has 1 slice allocated. And the namespace is kind of 3-1 distribution. Yeah. Okay. So this is from now, till now, I show you how this namespace scheduling work. Basically, leveraging the slice and based on the quota that the user specified, our scheduler will schedule the parts to schedule the namespace slices to different clusters and update the scheduling results in the placements. And currently the syncer has been changed, enhanced. So syncer will, every time they find the namespace, the tenant namespace has a change, they will watch for the change and check for these placements to see if the syncer's owner supercluster is in the placement list. If it is in the placement list, it will sync the root, the namespace to the supercluster, the corresponding supercluster. Yeah. Till now, do you guys have any questions?
This is super cool. I got one quick question. So with the slicing, what does that mean for the network space? I know when you originally wrote the doc on this, you talked about this basically negating the use of things like cluster IP and unless you have some higher level custom network that's able to operate that. I assume this fits into that same model where you end up still needing, like, every namespace now has to navigate through internal load balancers or however you operate cross cluster. Is that still the case?
Yes, it is. So the slice is kind of you can think of slice as a tuple of the resource that you care about. So for now, it's CPU memory. For instance, it can be extended to GPU because, for example, you can say that I want CPU memory and GPU is another number, right? So because assuming in the future, if you want to extend it, you need to extend the quota to CPU memory and something else. So this has a one-to-one correspond the one-to-one relation between the quota. Everything that you can specify in the quota, in the slice, you can use the same, the tuple. But for the networking, yes, the networking is completely orthogonal problem as of now. We should always assume you have a customized load balancer to do the kind of the service, to provide the service, to provide the services. You also need to make assumption, like in the sense that the entire supercluster, you need to have a way to do the routing across the clusters. This doesn't affect networking at all. It's purely like resource, like CPU memory, or can be extended to GPU.
Yeah, that makes perfect sense. Awesome. This is super cool. I'll let anybody else ask questions if they have them.
Yeah. Fei, it's a very good demo. It's a very exciting features. So I think there's still some complications. How we deal with the VN agent, like a kubelet reporting the status, where you have a lot of management to filter out different kubelet doing different parts. Because your schedule is one direction, but you need also all the time to getting this kubelet status from different clusters.
I haven't tried, but I thought the problem is as long as you, so here are a few things, right? So my syncer is currently installed in the meta clusters. My scheduler is currently installed in the meta clusters. But the VN agent need to be installed in as a daemon set in every superclusters. So if you think about this, if you remember my previous figure is like the pod, so think about that way. So as what I can say that if you, assuming that you don't have any network problems, so everything is a flat network. If you have a VN agent installed in the superclusters, and the rest of the model is still the old VC model, the syncer will copy create a V node in the tenant, right? We will give the VN agent IP in the tenant. So tenant, every Kubernetes code will still be direct to VN agent.
Okay. So still doing the same thing. It's not too overwhelmed, too much node to taking care, and got some bottleneck.
Bottleneck, I haven't fully thought about it. But if you look at the model that I'm currently using, is we still using one agent per node, one V agent per node.
Yeah.
Essentially, the load is how many paths it can possibly support, right? How many paths? But think of but that number of paths running in that node is kind of limited. It's capped by the node capacity, so it won't create too much scalability pressure, in my opinion. Because regardless of how big the entire system is, the number of paths one V agent is taking care of is still limited, like 100 paths.
So you're going to have a one VN agent for all the kind of yeah, okay.
It's still old model, one VN agent.
Okay.
Now I'm just thinking about the old model for VN agent, one VN agent per node.
Mm-hmm. Okay.
Yeah, so you're just expecting that every kubelet is still addressable by any control plane that's deployed in the meta cluster. Yeah. Is what you're getting at, which makes perfect sense. I mean, that fits the flat network model. And then if you wanted to, and I know we've talked about how this is less efficient, and I was just responding to a GitHub issue about this, but you could technically use the deployment route for the VN agent that we added that would expose one VN agent, load balanced VN agent per supercluster that you could do different policies around to kind of to abstract that more. If you didn't have a flat network, you could almost expose that VN agent. Again, this would be kind of insecure and you'd have to set up the policies properly, but you could expose one VN agent per scheduling cluster, per supercluster, and route through that using that feature flag that we added.
Yeah, the good thing is I didn't break the entire system is leveraging the VC model. So which means everything that you have been doing should be applicable in this model. Because that's the key. Everything that we have done so far, because I didn't break the syncer, so I didn't introduce a new API. Everything is just use native API, and the mechanism is still same. I'm still using synchronization mechanism. I'm still going to expose the V node to tenant master, so then you can play all the trick about which VN agent, so which proxy, which Kubernetes proxy. The request should go, because you essentially just manipulate the vnode IP address or part number, right?
Yeah, another question for Fei, that since we are getting into the scheduling domain, I think for the scheduling, user may think of there are some affinities, anti-affinities, or this existing scheduling feature, as well as how to handling preemptions. Yeah. So are we going to have some plugins in the future to that you are not rewriting all these scheduling features?
So here's the thing. So if you look at my repo, the scheduling thing is pretty much just empty. It's just like I'm just implementing first fit algorithm. So that can be extended. I think that is up to the users. Because you have a good references, which is a Kubernetes scheduler, you can try to you can enhance everything that you want based on how the Kubernetes scheduler does. Every affinity we can achieve affinity because it's like we can add all the labels in the namespace. If you look at my scheduler cache, I already trying to save all the labels, although it's empty. I'm going to keep all the labels in the root clusters. These labels of root clusters, you can add it to the cluster CR. Because in that CR, you can add all the labels you want. Then in scheduler cache, you have the labels for the root clusters. And in the namespace, if you look at if you add labels in the namespace, then it will show up here. So basically, you can still leverage the entire labeling system in the Kubernetes and do whatever things you want for them, affinity and affinity. The rest of the things is just algorithm implementation.
Okay.
For now, I'm just everything that I show for now is just a framework. Basically, enable the scheduling, just making people can do the scheduling work, just writing the algorithm and forget about the entire framework. So, for example, how do you update the cache? How do you handle the cluster offline? How do you handle the multi-cluster communication? How do you handle the cluster cache? Everything is done by the framework. So what I want to achieve, every user just need to focus on that algorithm directory and implement the algorithm.
Okay.
Okay, now I can show how the pod scheduling is done. I think I have one. Let me take this test deployment as an example. So in this example, I'm trying to use 100, and you have 4 replicas. So each replicas have 2. Okay. If you look at this one. See, you have 4 running. If you look at we'll see there is 1 running in root 2 and 3 running in root 1. Yeah, this is the schedule for the pod. Basically, based on this the slice distribution, the scheduler find that okay, there is the root 2, the cluster root 2 has enough capacity to satisfy this pod. Then it go to root 2. So this is the label annotation that the scheduler plays, and the syncer will watch for this annotation, and the root 2 syncer will sync this pod to root 2, and it's actually running. Yeah, this is how the pod scheduling is done. Okay, let me see if we have what this cluster cache look like. Yeah, the cache will have everything now. It has all the pods. Yeah, and this pods will show up root 2. We have 3 pods. Shows in the root 1, the cluster 1. Okay, so any questions so far?
Just
Nope,
a quick question on this. Can a pod cross the slice size? Meaning if a pod had the 200 millicores, would it just take 2 slices
No.
in its scheduling?
No.
Or
no.
is that that's the limit for a pod, is the slice size?
Slice size. the slice size is not the limit of the pod. So what I do is I'm going to sum, for example, if you look, I'm going to, for every cluster, I'm going to sum the size of all slices and do the scheduling. So for example, if I have, in this example, I have 3-1, I have 3-1. Let me show this. So I have 3-1, right? So in theory, you can run a pod with 3 slices in root class 1. My current schedule will allow that.
Okay, so we're able to create, even though we have 4 slices, we can create a pod up to the maximum number of slices that are available in a specific supercluster.
Exactly.
Okay.
So that, again, that's the power I allow you, because by placing with the slice size, you can somehow decide first the distribution or the max number, the max kind of pod size you can do. Again, this doesn't fit every usage model, but in general usage model, in the sense that in reality, the quota will be somehow more reasonable, is bigger than this 100 things, right? And the slice is kind of moderated slices, and you can your pod request should be also. I'm assuming in majority case you are running a workload, so it's kind of just the pods within the workload templates. I'm assuming you run 5, 6, 10 pods. So you can think of the slice size and the basically the quota slice size and the pods. I understand that there probably have some tweak things when you're setting up the slice size. But again, if you don't want to set it, I have a default. Anyway, this is the flexibility. For instance, you'd better, one best practice is you'd better, making the slice size and your quota size kind of a proportional. You don't want to have a skewed, configuration. Like, the slice doesn't, the CPU memory ratio, the CPU and the memory ratio in the quota is different than the CPU memory ratio in the slice, which is a bad example. Is that clear?
Yeah, makes sense.
Okay. Next, I'm going to show, I think the last one is I'm going to show how to do the cleanup. Yeah, the bad thing is the current Kubernetes, in this case, if you reduce a quota, the current Kubernetes doesn't kill the pods. I've tried. I don't know, which probably they just doesn't implement that. In my opinion, they probably should kill the pods. Either they shouldn't allow the quota to be reduced, or they should be able to kill the pods. But for now, what I observe that is that if you reduce the quota, for example, I run 4 pods, use up the entire quota. But if you reduce the quota by half, the pods is not going to be killed. So we have to take that the same. I didn't change that aspect. Okay, delete pods. Repeat the quota. Yeah, so if once you delete the quota, you will see that I'm going to clear the placement results from namespace. This namespace is this schedule. So what will happens in that the super cluster syncer will do the GC to remove the namespace, because this namespace doesn't belong to this class anymore. Let me see. But it will take some time. It's already gone. This may take some time. So it relies on 1 minute GC, the patroller, the 1 minute patroller to do the cleanup. The root one is already cleaned. See, it's terminating now. It's gone. All right, this is my end of demo today.
This is fantastic. Thanks so much for showing all this and being able to do it just off the cuff real quick. Cool. Well, we're basically at the end. If there's any other questions, pop them out real quick. Otherwise, we can call it, and we'll see y'all next week. And we'll look out for, everybody can look out for the next 2 pull requests that should be coming up this week for the controller manager and the nested control plane. And we'll get moving on CAPN stuff as well. Cool. Thanks, everybody. Have a great and wonderful week.